For this fourth part of the video series for electrostatic, we will talk about Coulomb's law. So Coulomb was studying the relationship that is between the two charges. So he was trying to figure out what is the electrostatic force that the two charges are interacting between each other. And intrigued by previous work, especially Newton's work, he was trying to find a similarity between the electrostatic force that the two charges are having and the gravitational force. And this is why he started to test and to complete the experiments with that is known as the torsion balance. You can check what is it. It's very similar to Cavendish that found the universal gravity G. And then based on this, he figured out that the electrostatic force between the two charges is direct proportion of the product of the two charges, the magnitude of the two charges, and the electrostatic force is direct proportion of the inverse squared of the distance between the two charges. Now, keep in mind, direct proportion in math doesn't mean equal, so you have to keep this into the consideration. So what direct proportion means is whatever you are increasing one side by, the same thing, the same increase will happen to the other side. So if you are decreasing the one side of the equation by a certain factor, the same decrease will happen on the other side of the equation. So it is the side, not each term in particular. So it's whatever you are doing, multiplying or dividing or increasing or decreasing by factor one side, the same thing will happen to the other side. This is the meaning of direct proportion. And when you put those two together, then the electrostatic force is equal to K Q1 Q2 over R squared, where K is that is known as the Coulomb's constant, and it is in your formula sheet, and it is 8.99. So okay, it's Coulomb's constant, and it is 8.99 times 10 to the power of 9. The units are newtons meter squared per coulomb squared. So when you put those two direct proportional finding that we have into the Coulomb's law, or what Coulomb's found, to make them equal, you have to add that is known as the Coulomb's constant to honor the work that he did, and it is in your formula sheet is 8.99 times 10 to the power of 9. So this is the Coulomb's law. Now let's see some applications of Coulomb's law when we have two charges that are at a certain distance between each other. So let's see example one for the Coulomb's law. Let's suppose that we have 2 point charges, charge 1 and charge 2. And charge 1 is, let's say, positive 5 coulombs, and charge 2 is negative, negative 3 coulombs. Now they are apart from each other at a distance of center to center, radius of, or distance of 3.2 meters. So now when we draw the free body diagram of what we are doing here is we are finding the electrostatic force of charge 1 is experiencing as a result of charge 2, and then charge 2 as a result of charge 1. So when we are drawing the free body diagram of the object 1, then we are starting by replacing the object of our interest with a dot. So this is for object 1. And then we see what is the force that object 1 is experiencing as a result of the presence of charge 2 or object 2. Since the two charges are opposite charges, then based on the general law of charges, they will attract each other. So this will be the electrostatic force that charge 1 is experiencing as a result of the presence of charge 2. And now when we draw the free body diagram of object 2, we replace the object of our interest with a dot, and then we see what is the force that the charge 2 or object 2 is experiencing as a result of the presence of object 1 or charge 1. And since they are opposite charges or unlike charges, then it is attraction as well. Now, based on the third law of Newton, we can say that the magnitude of those two forces is equal to each other and the direction is opposite. So, but again, they do not cancel each other because they are in two different objects. So we identified, when we draw the free body diagram on Coulomb's law, we identify the direction using the nature of the charges and the magnitude using the formula K Q1 Q2 over R squared. So in this case, the magnitude of the electrostatic force that object 1 is experiencing as a result of object 2 based on the third law of Newton will be the same as the magnitude that object 2 is experiencing as a result of the presence of object 1, and it is calculated as KQ1 Q2 over R squared, or 8.99 times 10 to the power of 9 times Q, so, and this is Newton's meter squared per Coulomb squared, times Q1 is 5.0 coulombs, 3.0 coulombs over 3.2 meters squared. So now coulombs and Coulomb squared, 2 coulombs are cancelled out, and this is affecting meter squared and 3.2, so meter squared and meter squared is cancelled out, and what you are left with is newtons. And now in your calculator you will find 8.99 times 10 to the power of 9 times 5 times 3 divided by 3.2 squared will be the force, that electrostatic force that the two charges are experiencing in between each other. And the direction will be defined by the general law of charges, that like charges will repel and opposite charges will attract. So you will have an electrostatic force that one is experiencing as a result of 2, or electrostatic force that 2 is experiencing as a result of 1 as 1.32 times 10 to the power of 10 newtons. Now let's suppose that we have two charges that are the same nature. So example 2. We have an object 1 that is apart from object 2 at a distance of 2.50 meters, and then the charge 1 is positively charged as 3.70 coulombs, and the charge 2 is as well positively charged as 4.80 coulombs. So if we draw the free body diagram of object 1, in terms of the electrostatic force, the object will be represented, the object of our interest will be represented by the dot, and then since we are dealing with charges, then we will see what is the force, what type of force is charge 1 experiencing as a result of the presence of charge 2, since they are the same, will be repulsion. So this will be the electrostatic force that charge 1 is experiencing as a result of the presence of charge 2. And when we draw the free body diagram of object 2, then we see what is the electrostatic force that charge 2 is experiencing as a result of the presence of charge 1, and that will be repulsion, because they are the same charges, same nature of the charge. And again, the magnitude of those two forces, even if you go with the calculations, you will have it, but based on the third law of Newton, will be the same, and they will be in the opposite direction. Now the magnitude of the electrostatic force 2 experiencing as a result of 1, or 1 as a result of 2, will be calculated as kq1 q2 over r squared, and then 8.99 times 10 to the power of 9. Now we are not writing the units because we know that the units will cancel out, and we are not even stating, when we are finding the magnitude, what is the nature of the charges for 1 and 2. We are just stating the magnitude of them, 4.80 over the radius we said is 2.50 squared. And now when you enter it in your calculator, you will find that the force that those two charges, electrostatic force that those two charges are experiencing is 2.55 times 10 to the power of 10 newtons. Okay, this will be the magnitude of the force, and then when you see as object 1 is going west, and when you see it from the perspective of object 2 is going east. Let's see another example. So example 3 of the application of Coulomb's law. Let's suppose that we are finding the electrostatic force that exists between the two fixed charges that are the two fixed charges that have magnitude of negative 7.50 times 10 to the power of negative 6 coulombs, and charge 2 as positive 8.70 times 10 to the power of 6 coulombs that are apart from each other at a distance of 0.040 meters. So it doesn't really matter which one is the force or the position of the two objects. So let's say that object 1 is here and object 2 is here. We have charge 1 as negative and charge 2 as positive charge. Now when we are drawing, we establish that the forces are equal in magnitude. Now when we are drawing the free body diagram of object 1, then the electrostatic force that object 1 is experiencing as a result of the presence of object 2 is attraction. So will be this one here, versus if we are drawing the free body diagram, then will be for object 2, then will be the opposite one. Again, it's attraction because they are opposite charges and they are equal in magnitude. We draw the free body diagram or the forces in terms of the electrostatic force. We draw the free body diagram in terms of the electrostatic force when we have using the general law of charges, saying that if there are opposite charges, then they will attract, and if they are same charges, they will repel. And we find the magnitude at one using the Coulomb's law, KQ1, Q2 over R squared. And we do not even state the sign of the charges now. So we just state the magnitude 7.50 times 10 to the power of -6 times 8.70 times 10 to the power of -6 over 0.040 to the power of 2. Enter this in your calculator and you will find that the electrostatic force is 366.6 newtons. And it is an attraction force. Okay, let's see another example. So, example, I think it is example 4. It is example 4. When we have two charges, say that we have two the same charges, so Q1 is at 7.0 times 10 to the power of -4 coulombs, and charge 2 is, this is positive and this is negative, so the same charge is positive. 8.0 times 10 to the power of -4 coulombs, and they are apart from each other at 0.17 meters. And each of those two charges have a mass, so mass 1 equals to mass 2 equals to, let's say, 5.3 grams. What is the acceleration that mass 1 is experiencing as a result of the electrostatic force? So we are omitting the fact that we have a force of gravity, but we are just taking into the consideration only the electrostatic force. So let's draw a situational diagram. We have charge 1 here that is positive, and charge 2 that is positive as well. So if we draw the free body diagram of object 1, we can draw object 2 as well, but object 1 will be fine. This will be a repulsion, so the electrostatic force, high repulsion because they are the same charges, and they are apart from each other at 0.17 meters. So let's find the magnitude of those of this electrostatic force. So electrostatic force will be KQ1 Q2 over R squared. So it is K times Q1 will be 7 times 10 to the power of -4 times 8, I think it is, yes, 8.0 times 10 to the power of -4 over, the radius is 0.7. Enter it in your calculator, you will find that the electrostatic force is 1027.3 newtons, which you can write it as 1.03 times 10 to the power of 123 newtons. And now, based on the second law of Newton, the acceleration as a result of the force of electrostatic force will be whatever is the electrostatic force over mass. So it will be 1.03 times 10 to the power of 3 over 5. I think that we said the mass is 5.3. Yeah, 5.3 times 10 to the power of -3. Divide by, it's 5.3 times 10 to the power of -3. And the acceleration as a result of the force of friction will be 1.94 times 10 to the power of 6 meters per second squared.